Now it is my pleasure to introduce Professor Erik Rosolowsky from the University of Alberta. Erik is an expert in the evolution of galaxies with a particular focus on their gas content. It is my pleasure to introduce Erik. His talk today will be entitled Atomic Hydrogen at the Crossroads of Galaxy Evolution. I now turn the control over to Dr. Rosolowsky.
Well, thank you so much for that introduction, Danny. It's a real pleasure to be talking to everyone today. I'm going to be talking about one of my favorite things in the universe, which is hydrogen, and specifically in nearby galaxies. But before we get going, I really want to say thank you to everyone and thing that has made this talk possible. Today, I have the privilege of presenting a lot of work that was carried out by my student, Erik, who's graduated and moved on to the Center of Astrophysics. But his PhD thesis work really got me interested in some of the questions that we're going to talk about today. I should thank Catherine Krekel and Francesco Santoro for providing some of the base graphics that I've used and remixed in this talk. You'll see references to OW on a lot of these talks, like et alia. And so I really am grateful for all my colleagues who have contributed to a lot of the work they have the good fortune of presenting. Today, I'm talking to you from Edmonton, Alberta in Canada, and that is located on Treaty 6 lands, which are the traditional homes and gathering places of the Métis and Indigenous peoples. And I should also acknowledge that I've received research support from the Canadian funding agency NSERC. So thank you to everything that made this possible. As a preamble, I wanted to talk about hydrogen and just kind of sort out when I'm saying different things, what I mean. This is a high school physics cartoon of hydrogen. In the center of your screen, you'll see here, this is a plot of atomic hydrogen, as you'd sort of see a proton and electron stuck together. And we'll call that often H1, which is a spectroscopic notation where that 1 is a Roman numeral I. If I strip that electron off of the proton, I get an ionized plasma or ionized gas, which I'll sometimes call H Roman numeral 2. Or the other thing I can do with hydrogen is to stick it together into two atoms to make a diatomic molecule, and we'll call this molecular hydrogen, or occasionally I'll slip up and call it also H, but this time subscript 2. And I promise you that this never gets confusing. With that preamble out of the way, I want to show you how galaxies form and evolve, or at least this is our best guess right now. This is a simulation of galaxy evolution generated by the illustrious TNG collaboration. The central panel that you're looking at here is showing you the gas as it's falling into the galaxy, and it's falling in under the action of gravity. And you can see it sort of streaming in from this cosmic web from the beginning period of the universe, evolving up to the current day. We won't go all the way to the current day, but this will show off what we're seeing here as, you know, how galaxies kind of come together. And the main physics that you should see is this material streaming in under the action of gravity. The lower left-hand panel is showing you the dark matter in the galaxy. That's what's actually setting where these galaxies are forming and saying this is where you should see the gravitational potential and fall down into. And in the lower right-hand panel, you see a panel for stars and a panel tracing out what the visible gas would look like. And so that's showing you how these galaxies are starting to really look like galaxies here. And with that sort of simulation, a lot of physics baked into this cartoonish view of galaxy evolution, we can actually start to ask some questions about this process. And so I take that simulated galaxy and I want to place it in the context of its halo, which is the surrounding material around it, and then sort of compare that to what we actually see in observations. And I can compare the gas that I see in that galaxy to the atomic gas that we make when we map a target. And so this sure shows a similar type of galaxy here mapped out in atomic gas. And a little later, I'll talk about how we actually make this map. And then I want to note that this is giving us a manifestation of what we actually see in the galaxy compared to the simulation that you see on the left. But this atomic gas is also setting the stage for another essential part of galaxy evolution, and that is the cosmic baryon cycle, which I've illustrated here. And that baryon cycle is talking about how we actually generate the stars we see in a galaxy. And we think this is a cyclical process by which we have this atomic gas collect and cool into molecular clouds, which then form stars. And some of the high mass stars in that population will go on, have relatively short lives, and explode in supernova explosions, returning their material to the interstellar medium. It'll cool and collect into the atomic gas and form a bit of a cycle here. This is, one of those aspects of galaxy evolution we'd like to understand. And then the connection back to the halo is another part of this. And so we think about how the material then connects, either driven by this baryon cycle or in atomic gas outflows to return material to the halo. And we also want to understand how material is coming in from the halo onto the disks of galaxies. And so these kind of represent the flow of matter into and out of the atomic interstellar medium. And that's why I like to call the atomic gas as the crossroads of galaxy evolution. And indeed, all of these connections, all of these roads that are coming together through the atomic ISM are relatively poorly understood. We'd really like to understand all of these. And when you saw that gorgeous simulation at the beginning of the talk, what that really is it has a lot of question marks buried in these connections. And they've made best guesses as to how these things are playing out. But our goal is really to start to understand the physics of these different connections. So how are we doing that? Well, I need to rely on an observational tool, and that's the H1 21 centimeter line. I've told you where the H1 comes from, but this 21 centimeter is coming from a specific hyperfine transition in the atomic hydrogen atom. And what's happening is you have the nuclear spin of the proton and the spin of the electron can be in two states, either aligned or anti-aligned. And the aligned state, because of magnetic interactions, is slightly higher energy than the anti-aligned state. And the photon energy corresponding to that energy difference gives you an observed frequency of about 1.4 gigahertz, or in terms of wavelength, about 21 centimeters. And so we have this great spectral line that traces just atomic hydrogen, traces it really well, and it gives us a sense of where the gas is in the galaxy. So we can go ahead and map that. Well, the obvious galaxy you'd think about mapping this is the Milky Way. And here's a map of atomic gas in the Milky Way. It's this thin little strip of color across the top of your screen. And what that's telling us is that we're really kind of stuck not being able to see the forest for the trees in the galaxy. But we've got a lot of good detail on individual regions, but we can't see the whole picture because we're stuck inside the galaxy. We get a little bit of insight here from a spectrum, and I've shown a spectrum of the 21 centimeter emission coming from one point in this map. And that's shown here in this graph in the bottom part of my screen. It's showing the amount of light I get, the brightness, measured as a function of velocity. And so the velocity I'm getting from the Doppler shift applied to the 21 centimeter spectral line. And so what we see is that this is a complicated spectrum. There's a lot of bumps and wiggles and little structures across this cloud. And what we're seeing is these are tens of different gas clouds along our line of sight. They're all projected on each other along this line of sight, and they're moving towards us and away from us. And this is leading to the observed Doppler effect. So we get some good insight from this Doppler effect and the fact that we're so close to the gas in our galaxy. But to get a good picture of how this is all playing out in the context of galaxy evolution, I contend that we really need to move on to external systems. And the nearest external systems are in galaxies in the local group. This is a map of our local group. The Milky Way is there at the center of these concentric spheres. And most of the observations I'm talking about are going to be happening between where we are in the Milky Way and some targets up here in this other kind of concentration of galaxies that we see. These are M31 and M33 are these relatively large targets. M31 is the Andromeda galaxy, and it's the other big galaxy in our local group of galaxies. And it kind of has a little sibling, M33, nearby it. And these are some of my favorite targets in astrophysics, just because they're so close and we get this top-down perspective that we can really study what a galaxy is doing in its internal details while having this bird's eye perspective. So it places a lot of things into context. But these targets are far away. And that 21 centimeters that gives us our emission line comes back to bite us in terms of resolution. You are probably familiar with this equation for telescope resolution, where the angular resolution of telescope is the wavelength that you're observing over the size of your optical instrument. And the 21 centimeter makes this, intrinsically a big number. So to get to high resolutions that we need to study the details of the physics here, we really need large instruments. And when you use interferometry, the relevant size is the separation between the antennae. And so all of the data that you're seeing is going to be coming from the VLA in New Mexico, which is pictured here. And I've taken this picture so you get its own, VLA at its own particular crossroads. But this instrument has really enabled a lot of the science that we're talking about. Here's an example of some of these images. This is a map of M31 in 21 centimeter emission, and every pixel in this map is a spectrum. So we've taken a spectrum that you see here, and I put out 4 representative spectra along these different lines of sight. And you'll see that there's a little less complexity in these spectra compared to what we're seeing in the Milky Way. So only a few clouds are showing up at these scales in this galaxy. So this gives us a little bit more kind of context where we can start to pick apart what's happening in M31. Since every pixel in the galaxy is a spectrum, we can also view this as a three-dimensional data volume. And so we call this a spectral line data cube. And I'm giving you a little bit of an animation here so you can see the structure of the emission inside our data. And the first thing that'll probably strike you is that there's this tilt to the emission. And that's from the rotation of the galaxy. One side, it's spinning, and so one side is moving towards us and one side's moving away from us. So we get a Doppler shift between the two sides. The next thing you probably notice is that there's a bunch of different rings here. It's not a very well-organized galaxy. And we think that this is a hallmark of the interactions between Andromeda and all those dwarf galaxies around it. And we think that this is giving us those connections, those very pieces of physics that you're seeing in the simulation when large pieces of matter come through the galaxy. That's what we're seeing here, the sort of echoes and residue of those kind of interactions. So there's a lot of information here and gives you a sense of what data we're actually working with. Next, what I'd like to do is talk about some of the pieces of this picture that we can get by studying the atomic gas in a galaxy. And the first one I want to focus on is this transition from the atomic gas feeding into the baryon cycle and the process of star formation. And we get that by comparing the atomic gas, and I've shown this here for the nearby galaxy M33 in the map of the red emission. So it's the background picture that you see here. On top of that, we're drawing a bunch of contours, and this is carbon monoxide emission taken from observations using the ALMA telescope. we're using carbon monoxide as a proxy for where the molecular gas is. So these are the clouds that should be forming stars eventually. And these are the scales of about 20 parsecs. So we're seeing individual star forming clouds here in the galaxy. And the first thing you'll probably notice is that those molecular clouds really seem to be connected to the atomic clouds. So they're really anchored to a cloud, with a few exceptions here or there. But we see a tight connection between the molecular gas and the atomic gas. And that tells us something right away about how molecular clouds are forming and how quickly they're forming. And we're then going, but the connection that we've made recently is really studying how the spectral properties of the molecular gas relate to the atomic gas. If we look across this galaxy, all of the molecular gas components are sort of single clouds. We see them as isolated, kind of single Gaussian components, sort of what you see here in the top spectrum. We know that the 21 centimeter components really don't look like that. They tend to be fairly complex, but we can always associate one molecular component with one hydrogen, atomic hydrogen component. And it tends to be the atomic hydrogen gas cloud that is tightly associated with the galaxy's rotation. All these other things are kind of off rotational velocities. And so we make this association between one molecular cloud and its envelope gas, which is something you can only do in these high resolution observations. And when we do that, we can compare the line widths. And I'm showing you the line width of the atomic gas here with this line width sigma. And if I graph the atomic line width, sigma, versus the molecular line width, CO, on the x and y axis of the graph here, I get this kind of complicated plot. And the complicated plot you see is showing you the focus here first on the contours of the emission. Or sorry, focus here on the contours in this plot. And that shows us the distribution of the data points here. And that shows you that on average, the molecular line widths tend to be about a factor of 2 smaller than the H1 line widths. And this is a prediction that's made by some aspects of molecular cloud formation. The other thing that you'll notice, and I'm sort of illustrated here, is that there are sort of clusters of points with different colored data here. And those different colored data are actually different regions inside the galaxy. So we're seeing that there is this relationship, but that relationship changes from place to place within the galaxy. One cloud has a tighter correlation, or sort of a 1-to-1 line width ratio between the atomic and molecular gas, indicating probably an earlier evolutionary state. And the stuff where the CO has sort of settled out to have a relatively narrow line width is probably a later evolutionary state. And so we're testing models that are quite popular for understanding this cloud formation using theories of cloud collisions or turbulent flows to understand how the atomic and molecular gas are connected. We really have good data to start to pick that apart. Another thing that we can look at is feeding the galaxy as a whole. So this is material coming in from the halo, and it shows up first in the galaxy in the atomic phase. And so we actually can observe structures that are coming into the galaxy, we think probably for one of the first times. And so that's, we can get a little bit of context for this by mapping out the 21 centimeter emission for this galaxy M33. And here we'll take advantage of some single dish observations that were made using the Arecibo telescope with really high sensitivity. And you see this dark ellipse in the center, that's the galaxy itself, what we've been looking at earlier. But if we go down to low column densities of hydrogen, you see this extended structure here that's a sign of the connections between this galaxy M33 and the broader cosmic web. And there's some structure to this halo atomic gas. And you can see one of these filaments here, it's sort of called out with this kind of peach colored highlight, connects to one of the structures that we see in our atomic gas maps. And so as filament kind of comes down, and at the end of that filament, we see this 10 million solar mass cloud of atomic gas that is hanging out. And the map on the left here is showing you the map of this structure, but we've used velocity information to filter out all of the components associated with the rest of the galaxy and just see that cloud. And on the right, you're seeing a spectrum of it. And it's this big, broad shoulder on top of the galactic disk emission, which has allowed us to pull this out. And so we think that given the offsets of almost 40 kilometers per second and the large scale cloud, this is probably something falling back or falling into the galaxy, maybe for the first time. These features are, that's not unique. We actually see a lot of these off velocity features, and they're these large kind of kiloparsec long filamentary structures. So we think that these are things that have gone up, circulated into the halo, or are falling into the halo for the first time, because it would be very challenging to get these kind of long structures by just sort of churning them up from stellar winds in the disk of the galaxy. So we think that this is actually accretion onto the system. The next thing that we can look at is how we can stir up the atomic gas in the galaxy using the baryon cycle. So really studying how material comes back into the atomic medium after spending some time in the stellar part of the baryon cycle. And here, we're again going to rely on the atomic gas line widths. So this is a plot that shows the atomic gas line width as a function of radius from the center of the galaxy. So 0 is the center of the galaxy, moving outward in the disk. And we've tried measuring the line width a bunch of different ways. And the trends that you see here show that pretty much no matter how we're measuring the line width, we see basically a flat trend. It's constant line width across the face of the galaxy. And this is interesting because you can take our measurements and directly relate them to the energy in the motion of the atomic gas. So the line width allows us to measure the kinetic energy, and I've given an expression for it here, 3/2 basically mv squared. That 3 is because the Doppler shift velocity is only giving us one component of the velocity of the gas. And so we add a factor of 3 to account for 3 dimensions versus 1 dimension. And then we use the line width for the H1 as a measure of the kinetic energy. And you can get the mass using some atomic physics and the brightness of the 21 centimeter line. Now, we can take that energy and make an estimate of the power that's lost in the galaxy because of turbulent motions. So this gas is sort of being stirred up and it's turning over in these turbulent eddies, and that's going to dissipate the kinetic energy at a rate that's fairly well understood. And we can plot that power dissipation per unit volume as a function of galactic radius here as this gray band. And so there's some uncertainty, and so I've plotted it as a range here. But then I can compare this to the energy injection that we would expect from a couple of different mechanisms. Supernova explosions, that's shown in the red line, or this magnetorotational instability, or MRI, is shown in the blue line. And what's kind of interesting is that none of these really can answer what is stirring the interstellar medium on a point-by-point basis. Supernova look pretty good on terms of an overall energy budget, but they don't quite have that flat profile that we see in the kinetic energy losses from the observations. So we're kind of given us a chance to test different ideas of how the interstellar medium is actually stirred using these methods. So this has given you a sense of some of the things we can do with these data, and I want to tell you a little bit about what the future looks like as we go forward with these studies. One of the things we can do is actually execute more detailed observations. These have all been kind of teaser results, and we can really kind of put the hammer down some final results if we execute some detailed observations. And to that, we formed this group called the Local Group L-band Survey. There's a large number of people involved with this. And the goal of our survey is to use the VLA, and we're executing a nearly 2,000-hour survey using the VLA ngVLA's amazing upgraded capabilities to study these 6 galaxies in the local group, the 2 that I've been studying about, and then 4 additional dwarf targets to find out what their atomic gas is doing, and a lot of other science. So this is going to be coming out over the next few years. And then beyond that, we have great opportunities moving forward with the 2 new facilities. At the beginning of the talk, you heard about the ngVLA, which we're well into the design stages for, and offers a great promise for executing similar observations here. And the key here is moving beyond the local group. I love the local group. These are some of the best targets in astrophysics, but we can carry out parallel observations in other galaxies that are more distant and really start to sort out what's the difference between galaxies with those observations. The other great facility here that's coming along is the Square Kilometer Array, and that's going to be able to study the 21 centimeter emission in good detail for a lot of these targets. It's now under construction. Here's one of the dishes. And so that offers a lot of good promise, and it actually gives a complementary view looking out onto the southern sky from Earth, and gives us a different set of targets that we could actually chase after. So these are some great opportunities for the future, and will really allow us to open up a lot of these questions of galaxy evolution from the study of atomic gas. Thank you all so much. I'd be happy to take any questions now.
What are the ranges of typical sizes of H1 disks in terms of R25 or other measures of the optical disk?
So they are typically larger by factors they're larger by factors that depend on your environment on average. So, but the general sense of it is that the H1 disks are going to be larger than the optical disk in the galaxy. And you can see the H1 emission farther out, and it's factors of kind of 1 and change to a few.
Yeah, my rule of thumb from grad school days was like 40% bigger than R25.
Yeah.
I had a question. You had a graph showing the line width is constant over the galaxy. That obviously must depend on the physical resolution. So what can you tell us about that?
Yeah, so it does depend on the resolution, and carrying these things out at larger resolution does sort of give you larger line widths. I mean, one of the big, I guess, obvious effects is as we went to high resolution in these galaxies, we started to see relatively smaller line widths. So on average, these line widths were smaller than a lot of the canonical values that you see. So we were seeing something like 7 kilometers per second, whereas a lot of your rule of thumb is probably 10 to 12 kilometers per second. And a lot of that has to do with the resolution of the observations. And if you smooth our data to larger scales, you of course see larger line widths. And we think we're starting to get into the case where actually tracing the sort of characteristic size line width relationships you should be seeing in turbulent flows. And one of the promises of really pushing this down to the best resolutions we can achieve with the VLA is starting to resolve out some of those turbulent cascade effects here, where we'll start to see this. We think we're matching fairly well to the thickness of the galaxies here and measuring kind of their full thickness of the interstellar medium on that scale.
Another question regarding your analysis of the supernovae effect on the H1. How do you differentiate the large line width produced by the supernova from the broad line due to the warm neutral medium?
So we kind of we don't. This is kind of input versus the output, and we don't look at sort of we don't look at kind of point by point supernova explosions, though, like in this analysis. That's something else we could talk about, and slides that I cut to get this down to a reasonable amount of time. So specifically what we're measuring here with the line width would be a characteristic warm neutral medium kind of line width that we then turn into a turbulent dissipation time scale by taking that and dividing the length scale by the line width. And so we use kind of a characteristic dissipation rate of an eddy turnover time in turbulence to come up with what the power dissipation rate would be. So we can also study wind-driven shells and supernova in detail to kind of understand how these explosions are coupling to the atomic interstellar medium.
We have a request if you could play the movie from the beginning again. At first glance, it looked like the visible disk got warped when stuff fell onto it. Is that what causes disk warping, or is that a wrong interpretation?
So I given this is the one that actually has falling in, so I think that's what it is. Yeah, so a lot of disk warps are thought to be coming from the interactions between the galaxy disk and all this stuff around it. Stuff falling in, stuff going by, creating sort of tidal distortions. And I think there's a pretty nice flyby here at some point. Where you can sort of see this. I don't know if I can recover this on the fly, but later on something goes crashing by and you can see some distortions in the disk. I got nothing, but we'll let this amazing thing run. Yeah, so you can see a bit of a warped disk here.
Yeah, it's fun to look at the video. You can either keep showing this or you can go back to the plot with radius. So one question is, are the wiggles and bumps and the line width variation with radius associated with spiral arm or other galactic structure?
So a couple of features, yes. So specifically in this galaxy, we see this kind of this modest rise here. That is where the spiral structure is most prominent in M33. And then it kind of dies off. There's not much amplification of these flocculent structures here, and it goes kind of flat and featureless once you get out beyond the place where you're seeing the, I'm not going to say full-on spiral arms, spiral structure, but at least the, these flocculent material arms developing in this galaxy.
Yeah. There are a number of theories that invoke, quote, gas accretion or gas transport as a source of turbulence. Can you comment on how well these may or may not work at explaining the radial turbulence profile?
Yeah, I think that's probably, that's probably the answer in the back of the book that we will want to chase, because it's the only these accretion-driven contributions are one of the few things that can inject a lot of energy at relatively large galactocentric radii. So I think that it's got to be part of the picture to have that. And yeah, we can start to look at that. It's not something that we did in this study, but it's certainly something we're after in the longer term.
Here's a fun question for you. What parts of parameter space are most severely limited by only being able to study local group galaxies at these resolutions for a full understanding of the star formation cycle?
Yeah, so that's you're asking for some of my favorite observing proposal text at this point. Yeah, so the local group, I mean, the reality is that, Andromeda is a relatively quiescent post-interaction disk galaxy that's probably well on its way to becoming a quenched system. M33 is, a beautiful disk, but it's totally just a dwarf galaxy with anemic spiral arms. One of the big questions that I'm excited about is how spiral structure in galaxies really drives a lot of these, the baryon cycle turnover. And here, there are other surveys that start to look at these a little farther out, to look at these dynamical feature like spiral arms and bars. But the big challenge we're facing there is we don't have 21 centimeter emission and a tracer of what the atomic gas is doing. We got great studies of the molecular gas. We have excellent understanding of the optical properties thanks to Hubble Space Telescope. James Webb Space Telescope's coming along is going to give us great embedded star formation estimates, but we're just lacking resolution to connect the atomic gas on the same physical scales that we have all these other amazing tracers on. So this is something that's like we're missing these dynamic features. there aren't really great starburst systems here, and we certainly haven't looked at things that are well along their way to evolving towards these quenched systems. So all of those require pushing out a little bit farther. The one thing we can do is low metallicity dwarfs pretty well, but low metallicity is not the only thing that represents sort of relationships to high redshift systems, or low metallicity is not the only thing that defines a high redshift system. And so, all of these questions and their application to long-term galactic evolution are going to require sort of picking up all the different pieces that make a high redshift environment what it is, and kind of putting them together by studying these different corners of parameter space.
Yeah, I guess I'd add, if you consider AGN having an impact on star formation, we don't really tap into that locally either. Yeah,
completely spaced, but that's a thing that we don't have a lot of AGN activity in the local group, or any going on right now. Certainly some relic evidence, but yeah, AGN are a major driver of galaxy evolution that we lack insight on right here.
Can you make any conclusions about the evolution of molecular clouds through the correlation between the CO and H1 line widths when the H1 is near the CO clump?
Yeah, so one of the things that I kind of in the interest of time, I swept under the rug in these sort of CO versus H1. I think this probably shows it off best, is that we don't just have individual clouds and individual spectra, and instead we have maps of all of these things. So the connections that we're really chasing after here are the profiles as a function of space. And the big phenomenon that we see here are these things that we broadly call velocity gradients. And velocity gradients can indicate a lot of things, but critically, they can indicate accelerating gas flows into these systems. And so that's how we're going to fold in the spatial information here. So we are well into the process of kind of pulling up what these things are doing spatially as well as spectrally to test these theories of molecular cloud formation.
Are there any signs of optically thick 21 centimeter emission?
Oh, I was gonna put this in as a backup slide. We recently carried out an analysis of this and put the results on the archive, and I can show you some of the figures from that paper. So something like this is a question as to whether the structures that you see here are a bunch of optically thin clouds along the line of sight, or is this an optically thick cloud, or are there signs of optically thick clouds? So we've seen rare instances of what looks like H1 self-absorption in our data. So a narrow absorption feature in the data. Are these features, large optically thick clouds? The analysis that we've done is that we sort of favor the interpretation where this is an ensemble of optically thin atomic gas clouds across the data here. So it's a complicated answer of these are probably not large optically thick atomic gas clouds with line widths of tens of kilometers per second. We do see a few cases of HISA, H1 self-absorption, but they're relatively rare. And so we don't have great evidence for widespread optically thick emission, but we do see a few isolated cases. I'll put as an addendum that something that we are excited to look at is some of the absorption line studies in the local group, survey. We'll get some really great deep observations towards background continuum sources, and this will open up the opportunities to do some absorption line studies, which is one of the best ways of understanding the opacity of the atomic interstellar medium.
Well, I'd like to thank everyone for attending, and special thanks to Erik for an intriguing talk, and hope to see you next week.